Welcome linear algebra fans, a video today on vector spaces. So after giving the definition of what a general vector space is, we'll see how things we've been dealing with fit in that context. We'll also see some examples of new vector spaces, things that don't really look like vectors but satisfy all the same requirements to be a vector space. We'll have a look at some properties of vector spaces, and then we'll see how those familiar definitions from the vector space of column vectors can be recycled into our vector spaces. So here's the definition. When V is a collection of things on which we've defined a way to add them and a way to multiply by a scalar, then V is a vector space if all of the following properties hold. So these should all be pretty familiar to us. We have familiar vector addition, closure under vector addition, and closure under scalar multiplication. We have commutative and associative properties of addition. There has to be a zero element. There has to be an additive inverse. And then we have all sorts of distributive properties for scalar multiplication. Okay, these are exactly the same properties that we required the vector space of column vectors to satisfy, and now we're just thinking about those same properties in more generality. So given a collection V and a definition of vector addition and scalar multiplication, we should check all of these above 10 properties to ensure that they hold, to make sure that V is a vector space. And of course, if any one of these properties fails, then it turns out V is not a vector space. So let's have a look at a few examples. Start with the familiar ones. So let's start with the vector space of column vectors. This is one we've already looked at. We know that that equality is defined component-wise. Of course, vector addition and scalar multiplication are also defined component-wise. And it turns out that when, and we already know this because we've seen this in our chapter on vectors, that all other properties hold, and this vector space of column vectors is a vector space, right? We've been calling it that, but it is. Okay, and the same is true for the vector space of M by N matrices, where elements are from the complex field. So again, equality component-wise, addition component-wise, scalar multiplication component-wise, all of those 10 properties hold, and this collection of matrices is a vector space. Okay, here's a new vector space, one we haven't talked about before, the set of polynomials up to and including degree n. So we define equality coefficient-wise, right? We say that P and Q are equal if all of their coefficients are equal. We can define vector addition coefficient-wise. P plus Q is defined as the corresponding coefficient of P plus the corresponding coefficient of Q. And there is a typo here. This should be B0, not B1. Sorry about that. And then, of course, scalar multiplication is also defined component-wise, right? This new vector, alpha P, is defined as the polynomial whose coefficients are alpha A0, alpha A1, and so on out to alpha AN. Okay, it turns out that all of our properties hold, in this case 2, and this collection of polynomials itself is a vector space. Here's another new one, the space of infinite sequences. So here's a vector space where elements in this vector space are lists of numbers, infinitely long, possibly. So we say that two elements in this collection are equal if all of their components are equal. We can define vector addition, and a new element of the space by summing components. And we can define scalar multiplication also by summing components. So all of the properties hold in this vector space of infinite sequences. C infinity is a vector space. Here's another new one, vector space of functions over any set capital X. So here, this is a collection capital F of functions little f that map this set X to the complex field. Okay, so we say that two functions in this vector space are equal if they're equal for all x in the set, capital X. Of course, we can define a new function by function addition, and we can define a new function by multiplying our function by a scalar. All of our properties hold. This collection of functions over any set itself is a vector space. We can talk about sort of a simple vector space, the vector space containing a single element. Okay, well, of course, if you only have one element, it's pretty quick to talk about equality, right? All elements are equal. We define addition kind of in a funny way, but the only way that makes sense, right? Since there's only one element in the set, z plus z has to be z. We can define scalar multiplication in the same way. For any scalar, alpha times z is z. It turns out that all properties hold with this definition of vector addition and scalar multiplication, and you might be getting a hint about what this vector space is. This vector space z is just the vector space containing the zero vector, right? That's really the only way to add a vector and get back yourself, or to multiply any scalar and get back yourself. So we'll circle back to that a little while later, the vector space containing only the zero vector. Here's another new vector space. This vector space might look like a vector space we've seen before. This is a vector space containing ordered pairs, where those pairs are complex numbers. So we say that functions are equal if they're equal component-wise, but we're going to define vector addition and scalar multiplication in sort of a strange way. So here's how we define vector addition. The sum of x plus y is the first component of x plus the first component of y plus 1. And we'll define the sum, and the second component, I'm sorry, is the second component of x plus the second component of y plus 1. We'll also define scalar multiplication in sort of a strange way, right? So alpha times the element x will be alpha times the first component of x plus alpha minus 1, and alpha times the second component of x plus alpha minus 1. It turns out with this definition of vector addition and scalar multiplication that this collection of vectors C is a vector space. We'll call it the crazy vector space because of this crazy definition of vector addition and scalar multiplication. So we'll go ahead and just verify a couple of these properties. So let's go ahead and check out, for instance, the commutative property of vector addition. So here's the first one, commutativity of vector addition. By definition, x plus y is defined as x1 plus y1 plus 1, x2 plus y2 plus 1. Now, of course, by a property of complex arithmetic, we can switch the order of y1 and x1 here. And this is just, again, the definition of y1 plus y plus x. It turns out that the zero element in the crazy vector space is the vector minus 1, minus 1. Let's go ahead and see that. So of course, 0 is a special element such that if you add 0 to any vector, you get back the vector you started with. So here I'll add 0 to the arbitrary vector x. Now, of course, by definition again, minus 1 plus x1, x2 is minus 1 plus x1 plus 1, and minus 1 plus x2 plus 1. Right, and of course those minus 1s come from the definition of the zero vector, and the plus 1s come from the definition of vector addition. Now, of course, those minus 1s, those 1s add to 0, and we end up with the vector we started with. Okay, so the 0 element in the crazy vector space is -1, -1. The 1 property works also, right? There should be a scalar 1 such that when you multiply by that scalar, you get back the vector you started with. So let's check that out. Okay, so here we see again by the definition of scalar multiplication that 1 times a vector x1, x2 is 1 times x1 plus 1 minus 1, and 1 times x2 plus 1 minus 1. Now, of course, those ones also add to 0, and we end up with the vector we started with. So as I mentioned, it turns out that all of these other properties hold. This crazy vector space with vector addition and scalar multiplication defined in this really strange way is a vector space. It's pretty cool. So there's opportunity for you to play around in the crazy vector space a little bit more on the worksheet, so check that out. Okay, let's talk about some properties of vector spaces in general. So here's one property. The 0 vector in any vector space is unique, right? There's only one 0 vector. I'll just state this without proof, but the way that one goes about identifying that a vector is unique is to assume that there are 2 and then show that they are the same. Okay, the additive inverse is another thing that's unique, and you show that the same way, right? You show that that by assuming there are 2 additive inverses, that those additive inverses are actually the same. So I'll just refer you to the book on those uniqueness proofs. Here's another interesting fact about vector spaces. Whenever you multiply any vector by the scalar 0, you get back the 0 vector. And similarly, if you pick any scalar and multiply by the 0 vector, you always get back the 0 vector. Okay, so that has to do with uniqueness of the vector too. A couple other proofs. The additive inverse is actually always just -1 times the vector u. And if you have alpha times u equal to the 0 vector, we use this later on, it's either alpha that's 0 or it's u that's 0. Okay, so keep that in mind. I won't go through those proofs, but they're in the book, so check those out. And then we'll go ahead and verify that a couple of these properties are true for the crazy vector space. Now we know that the crazy vector space is a vector space, so these properties must be true, but we'll go ahead and just check this out using vector addition and scalar multiplication as defined. So here's the first one, theorem ZSSM, that 0 scalar times any vector gives you back the 0 vector. So of course, by the definition of scalar multiplication, the scalar 0 times any vector u1, u2 is equal to 0 u1 plus 0 minus 1, 0 u2 plus 0 minus 1. Now, of course, by properties of complex arithmetic, 0 times u1 and 0 times u2 is going to be 0, so we get back -1 minus 1, which we previously saw is the 0 vector. Okay, let's check out the additive inverse too. Okay, on one hand, the scalar -1 times the vector u1, u2, by definition is -1 times u1, -1 minus 1, -1 times u2, -1 minus 1. So the result here is -u1 minus 2 and -u2 minus 2. Now, if we're claiming that this is the additive inverse, when we add this value to the vector u, using vector addition as defined, what we should get back is exactly the 0 vector. And it turns out you do. Okay, when I take the vector u1, u2, and I add it to minus u1 minus 2 minus u2 minus 2, right? By definition of vector addition in the crazy vector space, the first thing I get is u1 plus negative u1 minus u2 plus 1, and u2 plus negative u2 minus 2 plus 1. Now, of course, the u's add to 0, the scalars -2 plus 1 add to -1, and I'm left with what I know is the 0 vector in the crazy vector space. Okay, pretty cool. Okay, so again, there are some opportunities for you to play around with the crazy vector space some more on the worksheet. Okay, the last thing we'll do is recycle some of our definitions from previous, right? So in what follows, V is any vector space, right? So you could think of the vector space of column vectors, or you could think of the crazy vector space too, or maybe you want to think about the vector space of polynomials. So we can talk about linear combination the same ways, right? So given a collection of vectors from any vector space and n scalars, their linear combination is alpha 1 u1 plus alpha 2 u2 all the way out to alpha n un. Right, we can talk about the span of a set of vectors, all possible linear combinations. We can talk about a relation of linear dependence on a set of vectors, right? A relation of linear dependence, of course, is a linear combination that's equal to the 0 vector. And we can also talk about whether a set is linearly dependent, right? If there's a non-trivial relation of linear dependence, we call that set linearly dependent. Similarly, if there's only the trivial relation of linear dependence on the set, we say that the set is linearly independent. So what we'll see moving forward is that discussing all of these characteristics of a set of vectors ends up returning to sort of the same concepts from linear systems that we had before. So we'll be able to talk about linear independence of a set of functions or of vectors in the crazy vector space based on some ideas of linear algebra. Okay, folks, that's it for this introduction to vector spaces. I hope you have a good time playing around in the crazy vector space. So long for now. We'll see you soon. Bye-bye.